So, friends, in this video, I'll be talking about harmonic oscillator, and here I will only talk about the classical harmonic oscillator, the classical, and if we extend this harmonic oscillator, if we extend the classical idea of harmonic oscillator and modify it using some modified incursions, and we can see that there will be a transition of what we obtain from classical harmonic oscillator to what we will obtain when we will make use of quantum mechanical Schrodinger's equation on this harmonic oscillator problem. And everybody is aware about what harmonic motion means. This harmonic motion takes place when a system of some kind vibrates about its mean position. If I have a pendulum, if it vibrates from its mean position, so this is going to give us oscillations. We can have an example of a spring that oscillates, and the systems may be an object supported by a spring, or we may have something floating in a liquid, or a diatomic molecule. Okay. An atom in a crystal, we have crystal, an atom, it oscillates, so it can behave as a harmonic oscillator. So there are basically limitless examples on all scales of sizes where we can say that this is behaving like a harmonic oscillator. And the conditions for the harmonic motion is basically the presence of restoring force. So what's making it oscillate is the restoring force. So if I exert some force on this spring, it has a force that's opposite to the applied force. So this opposite force, what we call as restoring force, this is the force that acts to return the system to its equilibrium position, to its equilibrium configuration, whenever we disturb this oscillator, and certainly it is the inertia of the masses involved, because of them to overshoot the equilibrium, and the system oscillates indefinitely if there is no energy lost during the oscillation of that object. Now, if we try to take the special case of a simple harmonic motion, we have this restoring force, and if I assume that this restoring force is F, that's acting on a particle of mass. It is acting on a particle of mass, say m, and assuming it to be linear. That is, this F is proportional to the displacement of the particle. It's proportional to the displacement. Now this Y refers to the displacement. It refers to displacement from the mean position. It refers to the displacement from the mean position. And from its equilibrium mean position. Okay, so where it is where it has its equilibrium mean position, and certainly it acts in opposite direction. So when it acts in opposite direction, we think of writing down this as F is negative times some constant y, and this k here is called as spring constant. And this relationship is customarily known as Hooke's law. And we can write down this equation if we write down the force, and what's force basically is the double derivative of the displacement. So if we write down force here, so if we write down the force here, the force will be the double derivative of displacement with respect to time. This should be the case, and what we have is F is equal to minus ky, and For this f, I can use d2y by dt2, and this is equal to minus ky. Okay, so what we have is a second order differential equation. And here I have missed something because f is, it is mass into acceleration. So this is m times d2y by dt2. So here it is m times d2y by dt2. So what will be d2y by dt2 is minus k by my. And to write it in a precise way, d2y by dt2 plus k by my will be equal to 0. So this is a second order differential equation, and the solution of this equation can be written out in various ways. If we write down the solution, y is equal to some a and some cos omega t plus phi. And this omega is the angular frequency, and and we can write down this this omega is this omega is under root of it's under root of k by m. And if we convert this omega in terms of frequency, we will have 2 pi nu is equal to under root of k by m. And then we can have the frequency. That frequency that we will have here, it will give us the measure of frequency of oscillation. So what will be that frequency is, that frequency that we will have will be 1 by 2 pi under root of k by m. So this frequency is this nu is the frequency of oscillations, and this this a that we have, that a is the amplitude. So a refers to the amplitude. Now, as I have also introduced the phase here, the phase equal to phi, and the value of this phase phi, which is an angle, basically depends on what is y at the time t is equal to 0. So phi has a value, and it is dependent on the value of y at t is equal to 0, and certainly on the direction of the motion. Then at that time, what kind of direction of the motion will be. And to move on to the importance that we have, the importance of what we call this simple harmonic motion. It's this problem is important both in classical and in modern physics, and it certainly adheres. It certainly adheres back to the forces, back to the force that we have here as a restoring force. And that we interpret in terms of Hooke's law. And this Hooke's law, it happens to be true sometimes. It's not true always. It happens to be true under certain circumstances. So the point is to generate the circumstances where we can have the legality of this Hooke's law. That I'm trying to talk about. And in fact, that these restoring forces that are involved in the problems, they reduce to the Hooke's law for only small displacements. They reduce to Hooke's law for small y, for small displacements. And as a result of this, any system in which something executes, something oscillates, or something executes the small oscillations, the small vibrations about their mean positions, they certainly behave very much like simple harmonic oscillators. Now, to verify this important point that I was talking about, the applicability of this Hooke's law in a very, very small magnitude of the displacements that occur in these oscillations, what we perceive is that any restoring force which is a function of any force which is a function of say function of y, we can express this force. This y is the displacement. We can express this force in a mathematical series, what is known as Maclaurin's series. Maclaurin's series. And what is that? And this Maclaurin series is, we can write down it from the equilibrium position of some particular problem. So if we write down this Maclaurin's series, what we will have is I have f as a function of y, and I can write it as f at some y equal to 0. Then I will have df by dx at some x is equal to 0 times x, plus then I will have 1 by 2 of d2 of f by dx2 from x is equal to 0 and x scared. So it's all coming from x is equal to 0, plus so on and so forth. So this is how this restoring force can be interpreted in terms of Maclaurin's series. Now, what is the point of importance here is not the equation that I'm writing. What's important here is that at y, okay, sorry, I'm doing it wrong here. So my function is in terms of y, so it is y. So this is y is equal to 0, and this is y square. This is y is equal to 0. So this way, this force can be represented in terms of Maclaurin's series. Now, if this y is at y, we have at y equal to 0, we have the equilibrium position. So we have the equilibrium position. Okay, and at y equal to 0, f certainly has to be 0. That this f that we have, the part of the force that we have, this has to be 0. And for small y, the values of y square, y cube, y to the power of 4, they are very, very small in comparison to the value of y. For small y that we have. Okay, so we can neglect the higher order terms of this equation that we have. So we can write down this this whole series in terms of something that is significant to us, and that is this f of y is df by dx times, again I'm using y, df by dy times y at y is equal to 0. That's the case. Okay, so we have this this equation, which is basically Hooke's law. When this df by dy term that we have, when this df by dy term is negative, it's going to give us Hooke's law. And of course, it is for any restoring force valid that we have this equation, and the result is that in all the oscillations which are simple harmonic in character, and we have defined what simple harmonic means here, when their amplitudes are sufficiently small, then we can immediately think in terms of the potential energy of the function. And if I choose that potential energy as V of x, so I can think of potential energy. I can think of potential energy that corresponds to this Hooke's law, and we are in a position to calculate the work that's needed to bring this particle from y is equal to 0 to y is equal to y against such force. So what should I do for that case is I can calculate that potential energy, and that potential energy can be written down as that potential energy V of x can be written as negative of 0 to y f of y dy. So what can I have here is it's minus integral 0 to y, and for this f of y I can think of ky then dy, and what can I get out of it is this is equal to this will be k minus k square by 2 times y. So, so writing down the magnitude of this potential energy. So the magnitude of this potential energy is going to be 1 by 2 ky square. Okay, and this potential energy is, again I'm doing it wrong. Again I'm doing it wrong. I'm used to write down things in terms of x. I chose to write it in terms of y, and I'm committing mistakes in writing down the things. Now we can plot this equation that we have, and the curve that we can obtain for v of y, it would look something like this, because it's an equation of parabola. So it's gonna look like this. We have this and we have this. Okay, if I go right from here, now this is the position of maximum amplitude in one direction, and this will be the position of amplitude on the other direction. And let me assume this is plus a. And we can see that this is an equation of parabola, and if the energy of this oscillator is E, and then the particle vibrates back and forth from -1 to minus A to plus A, and this E and A are related by this equation that we have here, 1/2 of k ka square for maximum amplitude. This y is equal to a, and we can see the parabolic curve showing the continuous energy of this simple harmonic oscillator. Now in the next video we'll proceed from here, and we will try to inculcate some of the important arguments, not arguments, some of the important postulates of quantum mechanics to the same problem, and try to achieve the results. And certainly here we have what we have is we have this total energy, and we can see that it has all possible energies from plus A to minus A. So this is our classical harmonic oscillator.